All right, great. All right, guys, thanks for coming on. I think I'm going to get started here. So this is going to be a talk on DNS-based authentication by named entities. Just a quick show of hands. Who's ever heard of DNSSEC? Oh, great, good. And now, what about DANE? DNS-based authentication by name. Oh, wow. All right, great. So done this at a couple of different conferences and some mixed results on that. So it's good to see that people are starting to talk a little bit more about this. So a little bit about who I am. I'm Tony Cargile. I'm a security engineer at ISEC Partners. I carry out application infrastructure pen tests on various environments. I basically get paid to break stuff. It's pretty awesome. Before that, I was a developer in web application and configuration management environments, and then I graduated from UT with a degree in computer science. So I guess we'll just go over the agenda real quick. I'd love to just jump into DANE, but it's pretty hard to do that without a comprehensive knowledge of DNSSEC, and you can't really talk about DNSSEC without mentioning the problems of DNS. So we're going to go over that, and then I'll just kind of talk about what DANE addresses, how does it address it, and I know Heartbleed is so 3 months ago, but I will actually make a Heartbleed reference in this talk. So I guess we'll just go ahead and get started then. So domain name system, this should hopefully be a refresher for all of you, otherwise this talk might not go so well. But so what is DNS? DNS is a way for us to resolve www.google.com into an IP address so that browsers, servers, clients can all understand each other. So a simple customer client, this graph's actually kind of a bit contrived, but the client makes a request to a DNS resolver, then the DNS resolver recursively goes through the name servers till it finds the authoritative name server for the DNS record that it wants, and then gets the IP for that, and then it then proceeds to go to that IP for, say, www.bank.com. So what are some problems with DNS? First of all, it's pretty old. It's created before I was born. Berkeley created Bind in 1984. The RFC finally got ratified in 1987. So back during this time, security was a blimp on the radar. No one was really worried about their DNS traffic being spoofed or DNS cache poisoning or any of these issues that we have to deal with nowadays. So because of that, there's no integrity, no authentication, no confidentiality. And so the first problem with it, and it's really apparent, is you can just do spoofing on DNS traffic. So if you look at this example right here, this client makes a request to a DNS server, and it recursively looks up the DNS IP address for an A record. Now, if an attacker is somehow able to intercept that message anywhere in between the client and the name server, they could modify the traffic. There's no integrity, there's no confidentiality. So say a client wants to go to bank.com, they send a request for an A record for bank.com. The attacker realizes that this client is wanting to go to www.bank.com, but he instead replies back with the IP of his malicious server. So now the attacker has forced the client to go to his malicious server, and he can do phishing style attacks or really anything he wants with the victim. So that's like the most apparent problem with DNS, but then there's also the issue with DNS cache poisoning. So the first problem was that all that it really takes to forge a DNS request is the query ID that it takes in, and that's a 2-byte identifier for the request. So say an attacker or a client goes to a DNS caching server and says, I want www.bank.com. While that recursively is looking for that record for bank.com, it allows a window of opportunity for an attacker to send a request to that caching server saying that it's the customer, the client, And if it's able to match that query ID, then the name server goes, oh, okay, yeah, you wanted, I got the result for this, and now it shoots it back to the client, and it also caches that response. So now anytime any further anybody comes to this DNS caching server and wants the address for www.bank.com, now everybody's getting sent to a attacker name server. So this was a pretty old attack. The first solution was to just really lower the TTL on these requests, but really that's not like a great example for that, because DANE Convincey came out in 2008 and basically broke the internet by showing that by using subdomains, he was able to bypass those TTL restrictions by just using randomized subdomains, and he completely bypassed it. So the real solution that we're working with right now is using port randomization. So instead of all requests going over UDP port 53, the DNS server randomizes all of its available ports, and then so now not only do you have to guess the query ID for the DNS request, but now you also have to be able to guess the port that's running on. And so this adds a ton more entropy to it. It's not a perfect solution. I mean, you can probably tell that, you know, if you were able to just hammer away, you probably could sneak one through. Yeah, so that's basically DNS cache poisoning. So, and then there's some other issues with DNS, namely phishing style attacks. You know, you can register one sec partners instead of ISEC partners. They don't really ever check for that. You know, you can be Microsoft with a 1 in there instead of an I. No one's really ever checking for that. And also, you know, obviously the security of the DNS traffic is all about being able to protect your DNS server. And there's been known issues in DNS servers such as Bind. So that's kind of where we were with DNS before DNSSEC. And I think it's a really important point to note that this was what spurred DNSSEC. So what is DNSSEC? DNSSEC fixes a lot of the problems that was inherently with DNS. It provides origin authentication of DNS data, so we know that the person that responded to us is the person that we wanted to respond to us. We also can tell that there was, if we sent a request to a domain that doesn't exist, we can for sure tell that that domain doesn't exist. And finally, it provides integrity, so it's going to be taking basically an HMAC of the request and send it back to us with the request, so that we can tell that this request wasn't modified somewhere in the middle of all the traffic. Notably, though, it does not provide two things. It doesn't provide confidentiality and doesn't provide availability. And that's one of the big arguments against DNSSEC currently. So how does it do this? You know, that's a pretty bold statement to say that we're going to just fix DNS with this add-on. So what it does is it adds a few new fields, a few new DNS record types. So namely RRSIG, which is going to be able, so for each one of the records that's going to be in your DNS zone, you're going to also have a correlating RRSIG to that, which is simply going to be the signature of that DNS record. So for every A record in your zone, you're going to have an RRSIG record that's just a hash of that A record. Also, how are we going to be doing this hashing? Well, you're going to use a public-private key pair. The public key is going to be stored in DNS key, and also it's going to be stored on your parent zone. So I'm going to go over that in a few minutes, but basically you're storing it on your delegation server. And also it adds a few new record types for denial of existence, so it's that INSEC, INSEC3, and INSEC3 param. I'll go over that in a few minutes as well. But so how does it do the signing, right? Because that's going to be where all the security is in this protocol. And you have a few things here. You have your key signing key, your zone signing key, your DNS key, which is going to be your public key, and then your delegation server. So basically what you're going to do to protect your domain is you're going to create two public-private key pairs, the key signing key and the zone signing key, And so your zone signing key is going to be the one that actually signs the records. So you're using this private key to sign and hash all of those records that are in your zone. And then also you have your key signing key, which signs your zone signing key. And then you might think that's why that's a little redundant, but what that allows you to do is it allows you to rotate your zone signing key constantly without having to rotate your key signing key. And because of that, now you don't have to use your parent zone to upload your public key to your parent zone constantly. You can just, in your parent zone, it will say, hey, this is the public key for the key signing key. And then now in your zone, you're able to say, all right, so the key signing key is signed my zone signing key, and my zone signing key has signed this record, which creates that chain of trust. That can be kind of confusing, I can understand. This is kind of highlights a little bit of that. So the way that we can actually trust that these signatures are valid signatures is that down here, we get the A record for mybank.com as well as the RR-SIG for it. And that's signed by the signing key for mybank.com. But how do we know that that signing key is actually a valid signing key? Well, the public key for that is actually stored in the domain zone above it. So in this case, it would be your top level domain .com, what have you. And so that's stored there. Well, how do you know that what .com is sending you is valid? Well, that's signed by the signing key for .com, and then that public key is stored on the root DNS. And then how do you know that that is valid? Well, then it's signed by the root signing key, and then a DNS validator would have the root public key stored on files to pin to. So that's really what creates our chain of trust in DNSSEC. And that's really important to realize later when we go into some other stuff. So what does this look like? As a client, when you send a request, I know this is probably going to be a little small for you, so I'll just go ahead and jump to the bigger one. So a client sends a request to a DNSSEC implemented DNS server, and it looks extremely similar to what you would just see in a normal request. Just really there's one bit flipped that's saying, yeah, this is a request that can support DNSSEC. And so you just have a typical A request to using good.dane.verisignlabs.com since it supports DNSSEC. And then what do you get back? And this is kind of the interesting part. So what you get back is you get back two responses. One you'll see is the A response right here. That's just normal. But you also get the RR-SIG. And the RR-SIG tells you, okay, this is a signature for a record using SHA-256 with RSA, and here's the signer's name, and here's the signatures. So now we can actually take this signature and validate it with the public key that's actually stored on good.dane.verisignlabs.com. And again, we could use that chain of trust to actually validate that the record that we just got from this DNS server is the actual IP address that we wanted. So, like I mentioned earlier, there's some pros and some cons with DNSSEC. Obviously, the pros: no more DNS spoofing. We provided authentication and integrity, and so we can't do any more spoofing. We can't do any more cache poisoning. A big negative, though, is that we don't provide any sort of confidentiality with our DNS records. So, if someone was man-in-the-middling your request, they could tell that you're going to good.dane.verisignlabs.com. That isn't fixed. I noted right here there's a protocol called DNS curve using elliptic curve encryption. That's not really proprietary, but it's a non-approved protocol that handles this problem. So if you're interested in that, check that out. So why does this protect against DNS spoofing? So if you look at this graph, whenever an attacker is sitting in between the client and the DNS server, yeah, it can still modify those records, right? So if you send an A request out to bank.com, what you get back is the IP but how is that attacker going to sign that record type? And the answer is, unless he's got the private key, he can't. And so a DNS validator would just be like, the signature that you provided doesn't validate with the record that you provided, and so it just fails on that DNS request. So, like I said, DNSSEC takes care of DNS spoofing, pretty straightforward. So there was an interesting problem with DNSSEC when it first came out. So I didn't really go into this, but in SEC, what it does is whenever you send a request out to, say, baddomainname.google.com where it doesn't exist, when DNSSEC, what it does is it sends back a response saying that's not a valid DNS name, which is pretty helpful for clients to know that, okay, what you supplied isn't a valid name, instead of just not getting a response. But what it does is when DNSSEC first came out, it had a problem where it would tell you the domain before it and the domain after it. So say you went to, this is a server called ripe.net. If you went to e.ripe.net, which doesn't exist, it tells you, okay, that doesn't exist, but what does exist is 256cns.ripe.net and elearning.ripe.net. So you were able to simply just traverse through the alphabet and basically figure out where all of the valid domain names are in that zone. So INSEC 3 came along. This is a modification to the DNSSEC RFC, and what it does is it hashes. I don't know if you guys can probably see that in the back, but it hashes the name that we send. So whenever you send a request to e.ripe.net, it's going to hash that domain name and then check to see if it's valid inside of that. So we take care of that. You might think that's kind of a trivial thing, but like I've seen in the wild, and it's kind of crazy when you see passwords being stored in TXT records on domain zones. You can find some really interesting stuff in domain zones, so it's always interesting to do that. And so check that out. You know, if you see a domain that's got DNSSEC enabled, that's a great way to do zone enumeration. So that was a big problem that they kind of fixed with INSEC 3, but still we're relying on SHA-256 for those hashes. So technically, you know, if you had a big enough computer, you could probably break that. So, and another big complaint with DNSSEC is that it relies on this chain of trust, right? So your zone is signed by the parent in front of it, and then that parent in front of it is signed eventually by the root zone. And well, who owns the root zone? Well, the government does. IANA owns it. So that's a pretty big complaint by a lot of people, you know, trusting your sole security to just one computer, basically. And then the last problem, and it's the biggest problem with DNSSEC, is just the fact that it's implementation specific. So it was the root zone finally was compliant with DNSSEC in 2010, and .com finally got keys in March of 2011. But as you can see right now, here's a graph, and it's kind of small. But so this is 2013, and 2014, and this is the adoption rate of DNSSEC. And if you look right here, this is the green would be .com. This is .net, .edu, and at the .com we're right about 0.3% of all domains actually use DNSSEC right now, which is a pretty surprising number. And if you're ever interested, you can check out this website. https dnssec-name-and-shame.com. I'll probably post this on the slides. But go there, and you can see the Alexa top 100 of all the sites that support DNSSEC. Zero sites actually support DNSSEC right now from the Alexa top 100, which is incredibly surprising. And it's one of these protocols where it's a bootstrap protocol, right? No one wants to implement it because no one uses it, and no one wants to use it because no one implements it. And so, you know, the problems with DNS still exist in our current situation because nobody wants to take on the overhead of doing DNSSEC. All right, so finally we get to talk about DNS-based authentication by named entities. And why did I just spend 20 minutes talking about DNSSEC? Well, DANE sits on top of DNSSEC completely. It uses the security that's provided by DNSSEC to do one thing, and one thing simply, is to take away the sole reliance of security for the SSL sessions from the security authority and place it on the DNS server. So that's a pretty bold statement. So how does it do this? It uses a new record type again, a TLSA DNS record type, and so and it creates a record on the zone of a it's in this style right here. So it's going to be your port, your protocol, and then your domain name. So say this is HTTPS session on port 403, then this would be the domain name. And so inside this zone, you're going to see this domain name with a TLSA record. And so what does that TLSA record look like? It's pretty simple, actually. It's just 4 fields. 3 of them tell you the certificate usage, selector, matching type, and the 4th one actually tells you the data for that field. And so I'm just going to go through real quickly and tell you about these records. The first one is pretty simple. It's a selector field, so it's going to tell you, okay, in this record, oops, sorry about that. In this record, there's either the full certificate or this is just the subject public key info field. So you can actually supply either one of those. The next field is you can either give it the entire certificate or a public key field, or you can do a SHA-256 or a SHA-512 of it. This last field is actually like the most important field. So this is a certificate usage. So you can actually specify 4 different ways to use DANE right now. You can specify that the certificate that you're providing via either a full certificate or the SHA-256, whatever certificate you're providing is A. If you specify 0, it's a CA constraint. So you're specifying the root certificate that was signed for this certificate that you're going to subsequently get from the SSL session. And this certificate, it has to be validated by public key infrastructure. So it's going to be, wherever you use with like, Google or whatever right now. Field number or value number 1 specifies not only is this certificate that you're going to receive from this TLSA record, not only is it a valid PKIX certificate, but it's also the certificate that has to be the one that signed the HTTPS traffic. So you're actually pinning on a specific certificate. And then 2 and 3 are similar to this. So 2, you're saying that somewhere in this chain, this certificate was used, but it doesn't have to validate PKIX. And 3 is you specify a certificate that has to be the one that signed the traffic, and that also doesn't have to validate PKIX. So what does this actually look like? Again, this might be a little small, so I'll just jump right to the query. And so like I said, if a browser wanted to go to https://google.dane.verisignlabs.com, it would simply send a request to _403._TCP, that domain, with a type of TLSA, and then when it gets back is the record type. So we can actually look here and say, all right, so this is a domain issued certificate, so we're actually pinning on a certificate that doesn't have to be validated by PKIX. We're specifying the full certificate, and we're specifying a SHA-256 of this. And here is the actual hash of that certificate. And kind of a funny story, when I first got started with this project, I saw Wireshark, I was like, okay, they just specify the data here. They don't actually specify, like, they don't actually break it out. So, a great tool would be to add a dissector to Wireshark. But then I soon realized the rule of thumb is to always update your Wireshark before you start on running a dissector, because right after that, I updated Wireshark, and it handles everything fine for you perfectly. So good job on the Wireshark guys for being up to date. And then also next to that, you actually get the RSIG. So like I said, this sits on top of DNSSEC. So we know that the certificate that we just received is a valid certificate coming from the proper name server, and it hasn't been modified. So what does this do to our the way that we handle HTTPS traffic right now, right? So originally, what would happen is a client would make a request to the DNS server. The DNS server would give it back its IP, and then it would make a request to what it believes to be mybank.com. And now if this is an HTTPS session, it would make the SSL handshake first, make sure that's valid, and then make the HTTPS traffic. So what does DANE actually do in this situation? What it does is when this A record happens, it also kicks back with a TLSA record, which is a validated record. And so now the client knows what this handshake certificate should be. So if a DANE-aware client was to make a request and this server doesn't give it back the exact certificate that's been specified by this DNS server, then they know that it's that this isn't who it says it's supposed to be, and there's probably somebody sitting in the middle right here sniffing your traffic and intercepting your HTTPS requests. So this is what DANE's designed for. This is what it does well. But why am I talking about DANE? And like I said, the purpose of DANE was to take care of the problems with the CA system. And I'm just going to kind of go through kind of quickly because I'm running out of time here. But the CA system, there's some problems with the CA system, and I'm going to give you two examples before I go through and actually list out what the problems are. The first one, DigiNotar, in July 2011, an attacker was able to compromise DigiNotar and get a wildcard certificate for Google. He was able to create a wildcard certificate for Google. He then proceeded to use that certificate to man in the middle about 300,000 Iranian Gmail users. And also during this time, wildcard certificates were created for Yahoo, Mozilla, WordPress, and a bunch of other websites, some big name websites. So note these dates. July of 2010, the wildcard certificates came out. In August 29th, Microsoft finally revoked those certificates via CRL. That's about, what, like a month and a half? So another example, DigiCert Malaysia, not to be confused with DigiCert USA, two separate companies. DigiCert Malaysia was a intermediary CA for Entrust. So basically Entrust gave them a certificate that let them sign whoever they wanted. In July 2010. In November of 2011, they started just releasing bad certificates, just poor management skills. They started releasing 512-bit RSA keys, and they were missing a bunch of extensions and other parameters, and that would allow these certificates to be compromised. And they were issuing them to the Malaysian government. And so there was some investigation. They figured out what was happening, and finally, in November 17th of that year, Mozilla finally updated their revocation of these certificates. So again, 2 weeks after they realized. So these two examples kind of highlight the problem with the CA system that I see right now. One is that any compromise in the entire CA system compromises every single user that uses the CA system to verify trust. And two, once the certificate has been compromised, it's incredibly difficult to revoke that certificate. No one's actually doing it right now. And then, so how does DANE handle this? So, well, one, by pinning the certificate on the DNS and not the CA, you can completely bypass the chain of trust of the CA. You don't have to use it anymore. And also, it actually is a really elegant solution for handling certificate revocation. So I'm going to start talking about certificate revocation. Basically, there's two ways of approaching certificate revocation. One, there's CRL lists, and these are basically just large lists that browsers hold that have all of those certificates that have been revoked. But because of the problem of it being too large and there's just no way of having all of them. It's a fail open system. And similarly, OCSP is more of an online way of whenever a client receives a certificate, they're able to go on, make a request and see if the certificate has been revoked. But the problem is that it has to check every single certificate, and also it's all online, so no offline validation. And if you take down one of those OCSP servers, it's got to fail open. Otherwise, you just take down the internet, basically. So neither one of those solutions are valid, and your browsers don't really use either one of these completely. Chrome uses a kind of a modification of CRLs and OCSP. Most of your browsers do that. So the answer is that neither one of these actually protects the client from a revocation unless it's something that's like really highly publicized, like say DigiNotar. So for those playing Security Talk Bingo, let's talk about Heartbleed. So one of the byproducts of Heartbleed was that everybody wanted to revoke their compromised certificates. Everyone was like, oh, we've been hacked. So how does somebody like Chrome, like Google, handle millions of websites trying to revoke their certificates all at once? And if you actually go onto some Imperial Violet's blog, he eloquently states that they don't. They just couldn't handle it. There's no way that they can actually handle this many revocations at one time. And so a lot of them are still valid certificates that an attacker could use against each and every one of you right now. But with DANE, it actually handles certificate revocation extremely well. It's as simple as just replacing that TLSA record going onto your HTTPS server, generating a new certificate, and then just taking that certificate, putting it over onto your DNS zone, and simply re-signing your zone, and that's it. Your old certificate is no longer valid as long as you got to flush your DNS cache. So it might take about 48 hours, worst case scenario, to actually propagate throughout the DNS system. But after that, the certificate would no longer be valid. So this is really the meat and potatoes of this talk right here, and it's the little thing that I think each and every one of us needs to take into consideration, because there's two different ways or two viewpoints on this. And it's, do we want to put our trust of SSL traffic in certificate authorities, or do we want to do it in DNS servers? And so one of the great things about DNSSEC is, yes, it does use a chain of trust, but if if the bottom certificate was ever compromised, so say TonyCargile.com's DNSSEC private key was compromised, it doesn't ever pose a problem to, say, Google.com or any of other people that are in that zone. It's a chain of trust. It's not a web of trust. Whereas with the certificate authority, we've seen intermediary CAs have been popped countless times. It's to the point where we're at a web of trust, not a chain of trust in the CA system. And so I think that's really a pro for providing some security in a DNS server. And this one can be a controversial topic, but the certificate authority has multiple root anchors, multiple root CAs. And if you pay enough money, you can be one of those root CAs. Whereas on the DNSSEC protection, like I talked about, it's got one single root anchor, and that is IANA. That is the government. So there's pros and cons of both of those. Also, these root CAs, they're multinational companies. They're Symantec, they're GeoTrust. The people that are running these DNS root zones and the .coms and what have you, they're government agencies, or there's quasi-government agencies. That's kind of changing now, though, with the increase in generic TLDs. We're going to see it move more towards those multinational companies. But right now, we have Yeah, so in the multinational companies, we have 4 companies that actually provide 95% of the CA systems right now: Symantec, Komodo, GoDaddy, and GlobalSign. So, there's some pros and cons with that. Another thing that's kind of a problem with DANE is that, at least with the SSL handshake, it was like we're only dealing with one protocol here. It's just the handshake. We validate that the SSL signature is valid, and then we move on. With this, now we're having multiple protocols that are there to validate this this SSL session. So it adds a little bit more attack vector to it. There's more complexity to it. It's more difficult to do. So that's definitely a negative on using DANE. One thing though is how many CAs have been compromised, and how many certificates have been compromised, versus how many times have DNS servers been popped, and how many times have like .com or root zones been popped. So there's not really any hard stats on that, but as I showed, like DigiNotar, that's a root certificate authority that got compromised. So as far as I know, this root zone hasn't been compromised yet. So but the great thing is that, I'm saying these pros and cons versus certificate authority versus DNSSEC or DANE, but you don't have to choose right now, because if we go back to the slide, remember when I talked about certificate usage, we can actually pin not only on a certificate that we provide, but it also has to be validated by the public key infrastructure. So if we use certificate usage 1, if our DNS server gets popped, our CA system is still there to protect us, and if our CA system gets popped, our DNSSEC and DANE system is still there. So I think right now the best solution that we as a security community can do is to start using DANE, but start using it with 1. And that way we're able to slowly get the adoption rate for DANE, and at the same time still rely on the trust that we have with the CA system and introduce some more secure means to our SSL connections. So what is the worst case scenario? What happens, like where does DANE break down? And really the sole reliance is on that private key that's in the DNS server. So let's say worst case scenario, your DNS server gets popped. Well, what can an attacker do? Well, 1, he can't just re-sign his zone with a new CA certificate, because he would then have to proxy every single connection to that server with his own certificate. So basically it would just DOS the server. But what they could do is they could sit in between the, again, this would be like a normal client to server connection. He could sit here, and if he's got the private key so whenever this TLSA query comes back with that response, he could actually modify this request with the hash of his own certificate and update the RRSig because he's got that private key. And now what it would allow him to do is he's now able to use something like burp to provide his own CA cert. And now the client thinks that he's connected to bank.com whenever he's connected to an attacker that's sitting in this area over here. So, I mean, this isn't like ODay or anything like that, but this is just the worst case that happens. And you can kind of look back and see, all right, what happens if your CA or if your certificate's popped? Well, burp is pretty good at just being able to take that in. You can just take the certificate with the private key and public key in it, put it into burp, and now burp handles everything for you, and you're just proxying it. So there is some more steps to trying to use this compromise in DNSSEC versus a CA system. And actually I was up till about 4 in the morning last night trying to finish up a demo that I could show you of actually doing that, of actually proxying the traffic and rewriting RSIGs on the fly, but Python was just not liking me last night, so that did not happen. If anyone knows how to sign RR6 on the fly in Python, let me know. Yeah, so like I said, DANE has the same problem that DNSSEC has, right? With implementation, it's a bootstrap protocol. No one wants to use it because it's not been implemented. Hasn't been implemented because no one uses it. So there are some tools right now. Chrome used to have a DANE validator actually built into it, but they took it out because no one was using it. But you can still use this browser plugin called DNSSEC Validator, which actually, just provides two little boxes next to your URL whenever you go to a DANE validated website. So you can start using that right now on the 5 websites that actually use DANE right now. Like I said, like no one's actually using it. Like, there's 0.3% of the internet use DNSSEC. It's like maybe 20 websites that actually use DANE. So I've got it implemented on a subdomain of mine, dane.tony.cargile.com. If you want to test on anything with like validators, you can use that. It doesn't have anything important on it. It's like an Ubuntu test box. But and then also VeriSign Labs has basically the same thing on one of their sites, and you can actually go to bad.dane.verisignlabs.com and test for bad TLSA records. So there's you can test out some development. What actually kind of got me started on looking at this stuff is ISEC Partners parent company NCC is rolling out this new product called Domain Services, which is a generic TLD registering .trust website. So a company wants to have a website that's a little bit more verified, like say Microsoft. They want to do Microsoft.trust.com, or sorry, Microsoft.trust, to show that yes, their website is a little bit more trustworthy than their .com website. And the way that they do that is like NCC Domain Services would validate their identity. It would go through a set of rigorous security control policies. It would be actively tested by testers, and they would have to maintain this compliance while they held the .trust GTDLD. And the reason I started looking at DANE was because they're actually one of their policies is that they're going to be requiring every TLS session to have a DANE corresponding record with it. So NCC kind of sees that DANE is the future for security, and it's definitely going to be an example going forward. And if you're interested in this kind of thing, it's something that's going to be coming out here pretty soon. You can just do a Google search for NCC Domain Services and figure out everything you need to know about it. This is not a pitch for that, but I'm just trying to tell you that there is going to be some use of this in the future. So what can you do? You guys are just sitting there, yeah, this is all great stuff, but like, no one's using it. So what can you do? And if you're a builder, if you're a breaker, or if you're a handshaker, there's something that you can do. Builders, obviously, the most apparent people to start promoting DANE and DNSSEC. And these are website maintainers. So if you're running a website, why not sign your zones with DNSSEC, and why not start using DANE to provide some extra security for your website? And also application developers. If you're writing your application and you want some added security in your SSL sessions, then why not implement DANE, a DANE validator? It doesn't have to be a fail hard right now, but you can still have it as an added step in the security protocol. Breakers, people like me, this is actually an interesting point because people are going to start writing validators, and they're going to start writing checkers in their HTTPS stacks using DANE records. And so this is crypto stuff, so it's going to be native code, which usually means that if they're bad developers, you're going to find some bugs in them. And it's also going to be new code that they're going to have to rewrite for all these clients. So I definitely could see some bugs coming out of this. And actually, there was already a remote unauth bug in Bind, I think a year ago, having to do with TLSA record types. So there are going to be bugs when people start implementing this more. And handshakers, like I said, like 0.3% of the internet's using DNSSEC. We need to start educating upper management and people that have power in corporations and in government to start going, we need to secure DNS. We need some other way of doing that, and DNSSEC is probably the way of doing that. So we need to start educating people about DNSSEC and about DANE. All right, so yep, that's the end of my slides. I'm open for questions, or if you want to just meet me afterwards, I'll be standing out there. But you can get a hold of me via email. The slides and maybe some tools or stuff will probably be at isecpartners.com. Is there any questions? Yes.
Just a comment. focused on web, but it's really useful in the mail space. So
Oh yeah, SMT.
SDF records, VPN.
Yeah. And and DNSSEC works for any of your DNS records, so MX records as well. And like you said, DANE is for old TLSA session based protocols. So yes. CDN.
So, do you have any ideas of how you handle that? Because generally, like Comcast and Verizon, they will just spoof your DNS records if you don't have something wrong with them. I'm just curious if there's been any thoughts how you can handle that.
Well, like obviously, DNSSEC will take care of if they're going to be spoofing or rewriting your DNS tools. The one thing that I'd actually note about that, like you brought up with Comcast, is they're usually going to be your ISPs, right? So they actually, when you use DHCP on their systems, on their ISPs, you're going to be using their DNS resolvers. So using something like 8.8.8.8 for your DNS resolver, along with DNSSEC, could definitely take care of that situation. Did I kind of answer your? Oh, okay. I'm not too familiar with the problem that you're talking about. You're saying that Comcast is spoofing CDN IPs with their own IPs to take care of caching?
So let's say, and I'll use Akamai because I'm a little more familiar. They're going to put your certs on their servers anyways. And you can configure your DNS appropriately to account for that. So, I mean, it's a little extra work, but I don't think it's the bigger problem overall is not for more sophisticated people, it's the fact that most people are really scared of DNS. Bind is something that you love to hate.
Yeah.
And people just get it wrong all the time. That's the bigger problem.
Yeah, and luckily, kind of going towards that point, when DNS first came out, there wasn't really any tools. Like they came out with this RFC, and everyone's like, okay, yeah, it'll work. We could do this, and like we'll sign our zones, but there wasn't any tools. And now Bind comes with like a DNS keygen and DNS sign zone, which like helps, like it really automates it. So we're getting better towards that. But like you said, Bind's an unwieldy foe. But sorry, what's that? Yeah, question in the back. Yeah. So that's like a big negative towards DANE and towards DNSSEC is that at least with CAs, the more trustworthy ones won't let you register m1microsoft.com, but DNS servers really aren't DNS domain registrars are not that good at that. So that's definitely a negative. I personally haven't heard of anything about that, but if anyone else is, let me know about that. Really? That's pretty funny. Yeah. That's yeah. You could definitely see that. the big thing right now is like who knows where this protocol is going to end up, right? Because like it's not really implemented very well right now, and who knows where the client software is going to do with this? They could have it kind of fail open or fail close, and like if it fail closes and you have these technologies like this that are going to block these or try and modify these records at any point, it's just going to kill the internet if we have hard failed DANE client software. So that's like, I think that's also something that's kind of hindering adoption rates. Any other questions? All right, well, thank you for your time. I'll be in the hallway if you have any more questions.